All right. So let's do letter C. Let's do another derivative involving inverse trigonometric functions. Well, so here, number one, let's have a look at this one. Okay. Which differentiation rules are involved? Any ideas before? Yes.
Product.
There's a product rule involved. What else?
Chain rule.
Chain rule, right? So prominently, those are the ones that we're gonna have in this case. Well, so let's recall the product rule first of all. The derivative of a product u v, that's u prime v plus v prime u. In other words, it's the derivative of the first factor times the second without differentiating, plus the derivative of the second factor times the first factor without differentiating. So that's our derivative. So, and we're gonna apply this rule for the first term in the function, 2x arc cosine minus this crazy radical. And I know at the beginning this is gonna look crazy, but trust me, this will simplify really nicely. You'll see. Okay, before taking the derivative of this function, well, we cannot differentiate functions just right away when we have a radical. So let's use properties of radicals to write this in form of rational exponents. So that's the same as saying, so I'm not doing any calculus yet, just a rewrite 2x arc cosine x minus 2 times 1 minus x squared to the 1/2. Okay? And then from here we're good to go. So let's label the u and the v for the product rule. U and v. Okay? And let's use that product rule for that product of functions. Well, so what do we have? So u prime v, so u prime in this case the derivative of 2x, which is 2, times arc cosine. Oh, by the way, I would like to make a comment about one of your classmates asked about it looks like this looks like a negative, like a subtraction sign. No, it's a multiplication. So just so you guys don't get confused. And same here, this is also multiplication, not subtraction. So that's 2 times arc cos x, and then so that's plus the derivative of arc cosine, which, okay, let's go back to the derivatives of the inverse trigonometric function. The derivative of arc cosine, it's very similar to the arc sine. It's exactly the same except for the sign. It has a negative in the arc cosine function. And so plus the derivative of arc cosine, which is -1 over the square root of 1 minus x squared. Okay, so that's the derivative times 2x. All right. Okay, let me label, just so this doesn't look mysterious when you go back and review this. This is u prime v plus v prime u. So that's the product rule in action and properly labeled, just so you can see where is everything coming from. Okay. And then we need to take the derivative of this. We use the chain rule here, so that's minus 1/2 times 2, 1 minus x squared to the 1/2 minus 1, which is -1/2, but in this case times the derivative of the quantity inside of the parentheses, which happens to be -2x. Okay, well, there's a bunch of cancellations here and rewrites. Let's take care of the rewrites, well, some cancellations as well. So f prime equals, so that's 2 arc cos without the multiplication symbol here, no need to. And well, this is going to be -1 times 2x, so that's -2x over the square root of 1 minus x squared. And then from here, let's cancel these 2's, and this negative right here times the negative that came from using the chain rule will turn the last term into positive, and that's 2x And I'm going to send this factor right here to the denominator with positive exponent. And then I'm going to go back from rational exponent notation to radical notation. And you'll see what's going to happen here. 2 arc cos x minus 2x over square root of 1 minus x squared plus 2x over the square root of 1 minus x squared. Cancel these two terms, and our final answer is simply 2 arc cos x. Okay? I mean, of course, we could make up a lot of exercises here, putting this together with quotient rules, with exponentials combined with inverse trig functions and the like, right? But now we're going to move to the integrals involving inverse trigonometric functions. So no, we're not going to integrate arc sine. We're not going to integrate arc tan. We're not going to integrate arc secant. In fact, we're going to integrate some functions in terms of radicals right here that produce, inverse trigonometric functions. In fact, to evaluate the integral of arc tan, for example, we don't have the tools yet. We need integration by parts, which is coming in the 3rd week, I think. Okay. So, but we're gonna see this. Okay. Well, so let's evaluate this integral right here. So, pretty much what we have to do is observe the form of the integral, because notice how, okay, let's compare the first two integrals, the one that produces arc sine and the one that produces the arctan. So, and actually all of them involve a sum or a difference of perfect squares, right? Well, but in this case, one of them is under the radical. The arctan is not under a radical, it's just itself. Okay, so in this case, if we try to compare the first integral with any of the forms, which one would be the best one?
The first one.
The first one, right? Arc sine, yes. Yes, be careful with the one in the denominator. It has reverse order u squared minus a squared, and it has a u outside. All right? And well, number one, it's important to do some labeling here, to do some rewrite. So I'm going to rewrite the integral first to make it look like the one in the form. So this integral of 2 over the square root of 16, which is the same as saying 4 squared, minus what quantity squared produces a 9x squared? 3x, correct. With respect to x. So, well, actually, I'm going to take the 2 outside. So in this case, we do this with the following purpose: to identify what u is, which in this case u equals the 3x, and du equals 3 dx, right? So that's so we can perform the substitution. And in this case, well, we want to solve for dx. Dx will be 1/3 du. Okay? So in this case, we're going to go back to the integral. That's going to be 2 times the integral. Instead of having a dx, this will be, well, number one, the radical is 4 squared minus u squared times 1/3 du. So let me take that that 1/3 outside to multiply it with the 2. That's 2/3 integral of du. And that's the square root of 4 squared minus u squared. And that's 2/3 the coefficient times arc sine of u over, in this case, a. But it would be a good idea to also label a equals to 4. All right? So that's my advice, to label all of them. So when you use the correct formula, in some cases we need the square, in some cases not the square. So u over u over a, and don't forget the plus c. So back substituting for u and a respectively, that's u, which is 3x, over a, which is 4, plus c. And that's the final answer to the integral. All right, letter B. Well, letter B doesn't have any radicals. And in fact, if we observe, some of the terms are exponentials. Those exponentials were not in the basic formulas at the top of the page, are they? However, we can still interpret this integral the following way. So, okay, let me rewrite the integral of e to the x over 2 squared plus e to the x quantity squared dx. And well, in this case, if we rewrite u equals e to the x, what's du? What's the derivative of e to the x? E to the x itself, dx, all right? But we also find what a is. In this case, it's 2. Okay, so what do we have? Oh, no, that's fine, that's fine. Okay, so this e to the x dx will become du. Du over a squared, let me write it as a squared plus u squared. Okay, now that we see the integral in terms of a's and u's, can we compare with any from the formulas at the top of the page?
2.
Number 2, it's going to be the arctangent rule, right? But be careful. The arctangent rule has a 1 over a arctan u over a. So that's going to be 1 over a arctan of u over a plus c. And in this case, let's back substitute not just for u, but also for a. So that's 1 over a, which is 2, arctan of u, which is the exponential e to the x over 2 and plus c. Okay? Letter C. And well, letter C, it's a little fun. It's a little funky one. And yes, I know this one, it's not gonna be very straightforward, because well, if we observe the radicand, that is the quantity inside of the radical, we have an x minus 4, all right? Which doesn't look like a difference of squares. In fact, the only perfect square is the number 4 in there, not the x, all right? However, well, we can use a trick and make this look like a difference of squares. Why not? There's tricks here and there. For example, this x can be anything pretty much. You can rewrite it your favorite way. On the one hand, for example, this is the square root of x squared, right? Because the square cancels the radical, or it could be the cube root of x cubed, or the 17th root of x to the 17. You know, we can rewrite this in your favorite way, in the preferred way you want. However, we're going to rewrite it in a way that we need it for this integral right here. So in particular, I'm going to rewrite this integral. That's okay. I'm going to take the 5/3 outside of the integral, and well, I'm going to leave a space for this x right here. So that's going to be the square root of x quantity squared minus 4, or rather 2 squared. Okay, so from here Well, if let me leave the x, but don't write the x. I'm just going to write it, but don't do it yet. So, if I observe this integral right here, I have some u squared minus a squared. It looks like this fits the arc secant function, right? However, in this case, we have a u squared, and we need to have the square root of that quantity outside multiplying the radical. Now, if we observe this radical is the square root of x, its square root, is that actually x? In fact, it's square, not the square root. However, the trick here is to rewrite this x because, for example, okay, let me do the u du setup. If I set u equals to the square root of x, which is x to the 1/2, du is 1/2 x to the negative 1/2 by using the general power rule, dx. Okay? And simplifying this to positive powers and radicals, that's du 1/2 x to the 1/2 dx. And let's go back to radicals, 2 root of x dx. So when we compare the u du, notice the x radical x. Let's compare here dx. Oh, we don't have a radical x in here, right? But we can use a trick to turn this x into somehow radical x. So let's go about that part. Okay. Okay, again, let's play with that x. That x, another way to interpret, well, so this x can be, I don't know, maybe x squared times x to the negative 1. 2 minus 1 is 1, back to x, right? Or x to the negative 17 times x to the positive 18, right? That's another way to write the variable x, but in this case we want to aim for something that contains radicals, and in fact this happens that x is root of x times itself. All right, and this is because this is x to the 1/2 times x to the 1/2, and what do we get when we add a half plus a half? 1. Isn't that the same as x to the 1? All right, so let's replace this x right here. Root of x, root of x. I'm going to highlight the part that will stand the u du part. And in fact, okay, yes, I need to solve for the radical first. For this part. I need to move the 2 du equals 1/root of x dx. Let me highlight all this. And the reason I'm highlighting this is so you can see how I will do the substitution in the next step. So that is dx root of x. So these two are going to become 2 du.
Wouldn't it be
du over 2? Oh, no, because in this case the 2 is in the denominator. It would be multiplying. Yep. So what are we going to have? Okay, on another note, okay, another highlight actually. This radical x is going to be our u, along with this radical x. Okay, let me go back to the formula. We want u squared and a u outside, a sole u, right? This is u quantity squared, and this is the sole u in this case. Okay, so we're ready to do the substitution in this case. So that's going to be 5/3 the integral of 2 du over u times the square root of u squared minus a squared. And well, recognizing the form, okay, let me have the coefficients outside. So that'll be 5 times 2, that's 10 over 3 integral of du over the square root of u squared root of u squared minus a squared. Now that we have the integral in terms of u and a, this integral fits the arc, the one that involves arc secant. So let me write it in terms of a and u. So that's going to be 10/3 1 over a arc secant of the quantity absolute value of u over a plus c. And now let's go back, substitute for what we had for u and what we had for a. So that's 10/3 1 over a. In this case, a, I didn't write what a is. Let me write it down here. A equals to 2. And that's 1/2 arc secant of, in this case, okay, notice the formula, the integral formula right here involves absolute value of u, okay? However, not in all cases it's necessary to have those absolute value bars, and in fact this is one of those cases because, well, what's the domain of the square root of x function? 0 to infinity. So will the radical x output negative values that we need absolute values to fix that? Well, not in this case, so we just write square root of x over a, which is 2, plus c. And 10 over 2, that's 5/3. That's 5/3 arc secant of root of x over 2 plus c. However, if our u were something like x cubed, you know, a function that outputs both positive and negative values, then we would have left the absolute value bars in here. All right. Yes, I'm not gonna lie. This integral in letter C is kind of funky. Required to. It's a little involved in the sense of the algebra that we did. But don't worry, I'm not gonna give you anything like this on the exam. And I don't think there's anything like this in the homework. But sometimes it's good to look at problems like this to put together all this. You know, all these tools that we have from past courses like algebra, calc 1, etc. Okay? All right. Let's look at a very, very classical problem, one that for sure will be an exam question. Yeah, so let's see what about this one. The integral of 2 over the square root of negative x squared minus 4x. Well, at first glance, the quantity inside of that radical doesn't look anything like a difference of squares or a sum of squares, does it? I mean, except for the first term, negative x squared, but that for x, it's not a perfect square other than its coefficient. It has to be the whole thing in order to be a perfect square, not just a 4x. Well, in this case, the strategy that we're going to use for this integral is completing the square, all right? So, well, I'm going to take that completing the square on the side. That's going to be negative x squared minus 4x. Well, so we need to add and subtract a number that produces a perfect square trinomial that gets factored, and well, the rest of the story you'll see it in a second. However, we need to be very, very careful when completing the square on a polynomial. We need to make sure that the leading coefficient, or rather the leading term, that is the term that contains the x squared, doesn't have a coefficient at all. And in fact, it is implied that there is a -1 coefficient, which I will factor out. So let me factor x squared and then plus 4x. Okay? And well, so I'm going to work with this binomial to turn it into a perfect square trinomial by adding a blank. This blank right here, it's a magical mystery number that will complete the square, that will turn this into a perfect square trinomial. However, be careful, because we cannot just add numbers to an expression, because if I add a number, then I will be changing the integrity of the value of the expression. So we need to do an undo in this case. For example, but be careful, how do we do an undo? Typically when we have x We can add 4, subtract 4, that's still x. Alright? In this case, be careful, because we're adding a number, but we are not really adding it. Do you see what we're really adding in this case? We're really subtracting it, because this plus number is being affected by the negative in the front of the parentheses. So if we're subtracting, then we need to add, to do the opposite, which is add. So I'm going to add a number. Okay, let me add the number. Well, how do we find that magical mystery number that completes the square? So it's always the middle coefficient divided by 2 and squared. So that's 4 over 2, which is 2 squared, which is 4. 4 and 4. All right. And let's see. So now that we have this perfect square trinomial, x squared plus 4x plus 4, we should be able to factor it. So that's going to be, okay, let me move on over here. So that's going to be negative x plus 2 quantity squared. So how did I factor this trinomial? When we add this magical mystery number that completes the square, this is guaranteed to be or to produce a perfect square trinomial. And to factor that, it's the square root of the first term, that is the square root of x squared, which is x, the square root of the third term. What happened here? I think I press on the X accidentally. Okay. Yeah, that's what happened. And then the sign of the middle term. All right, and then the whole quantity squared, and plus 4. Whoops. And rewriting it in the correct order, this is 4 minus x plus 2 quantity squared. So we may go back to the integral. And let's see, now that we have this integral right here, can we relate the form of the integral to something that we had from the top of the previous page?
Arc sign?
Arc sign, right? Sorry about that. Okay, arc sign with u equals to x plus 2 du, which is simply the x, and let's state the a in this case. A is a quantity whose squared is 4 in this case, that is a 2. So 2 times the integral of du and this is going to be arc sine, 2 arc sine of u over a plus c. What's u again in this case? X plus 2 over 2 plus c. Questions about this exercise? Let's look at one more. How about a definite integral? Oh, we haven't done a definite integral. Okay. Any ideas on how to go about this integral? Interesting. What would be a good method to evaluate it?
Quotient rule?
Quotient rule, well, that's for derivatives. So quotient rule is for derivatives, and there's really no quotient rule for integrals. So would U substitution work here, or one of the integration rules that we've been using throughout these few exercises? It looks like U substitution because, well, in this case, we have arc cosine. If we take that as our U, the derivative, well, it's sort of there, 1 minus x squared, but except for the negative sign. But of course, we can fix that in the U du setting. So let's go ahead and do that. So number one, U equals arc cos x du equals negative 1 over the square root of 1 minus x squared dx. But to get this together with the part that send the du and the u part, let's move the negative to the left hand side. Du, that's dx over the square root of 1 minus x squared. Okay, so that's well, I'm going to write this as the integral of negative du. Oh, no. It's negative u du because of the negative and the du. And I'm going to take that negative outside to make this easier to interpret. And well, all we're doing is integrating u using the general power rule. This is u squared over 2. And in this case, negative arc cos of x squared over 2, and in this case, because this is a definite integral, goes from 0 all the way to 1/2. So we need to evaluate, in this case, use the fundamental theorem of calculus, that is, evaluate at the upper limit minus evaluate at the lower limit. But let me rewrite this in a more friendlier way. That's a negative 1/2 arc cos squared x. All right. So from 0 to 1/2, negative 1/2 arc cos squared in this case, arc cos squared of 1/2 minus arc cos squared of 0. Let's evaluate this, and what do we get for arc cosine of 1/2? In other words, what angle has a cosine of 1/2? Pi over 3, so that's a negative 1/2. So that's pi over 3 squared minus what angle has a cosine of 0? It's pi over 2. Pi over 2. And let's square these numbers. No need to simplify them all the way. Negative 1/2 times pi squared over 9 minus pi squared over 4. This is an acceptable answer. Okay. I know, I mean, we could find LCDs, combine them together, but this is fine. Let's see what's on the next page. So the next couple of exercises here. Okay, so evaluate the two integrals below. Think about how are they similar or different. Well, I really don't want to go through evaluating the integrals to just see the difference. So the only difference here is we have an x in here, and here we don't have an x. In this case, u sub will be fine. And in this case, we can use one of the rules that we just looked in this couple of pages prior, right? I think the one that contains the sum of squares, I think it's the arctan rule, right? That's going to be a good fit for the arctan rule with u equals x, a equals 3, du dx. So that's the integral of u squared minus a plus a squared and du, and this is 1 over a arctan of u over a plus c, where a is 3 1/3 arctan of u over a, which is x over 3 plus c. For the other one, it's just a basic u substitution where u equals x squared plus 9 and du 2x dx and x dx equals 1/2 du. So let's just do the substitution to get, what's this going to be? So that's the integral of, in this case, that's a 1/2 du over u, which is 1/2 the integral. And what's the integral of du over u? It's one of those. Which one is it? ln. All right, that's 1/2 of typically ln of absolute value of u plus c, right? But in some cases, it's not necessary to have those absolute values, like this particular case, because we have x squared plus 9. And whether you have a negative or positive x, because it's getting squared, it's always going to be positive, so no need for absolute value bars in this case. All right.